Welcome to this week's lecture of Introduction to Structured Programming. We are already in week 6, and again we are talking about pointers. I think it's now the third time we are talking about pointers, and it's the last time it's our main topic because next week we are switching to memory.
But we will use them, of course.
But we will use pointers, of course. But today is, again, all about pointers. So we will have arrays with pointers, we will have application of pointers, and many, many more things. But before, as always, let's talk a little bit about organizational methods. There is not much for today. We have our handout of the weekly exercises today after the lecture. It's the 6th weekly exercises, and they belong to assignment 2. So they are also the last one who belong to assignment 2. Next week already belong to assignment 3 then. So as I said, the last exercises for assignment 2, the deadline is for the exercises is the deadline for assignment 2. It's the 19th November. And just as a reminder, if you do not complete more than 50% of the exercises, you will get a 25% point deduction. But I think it's 6 exercises.
I think even 7.
7 exercises,
yeah.
So you have to complete 4. Yeah. I think that's doable.
Definitely.
Okay, before we start with the recap, I just want to give you a short idea of real usage of pointers, because I always hear the question, why should we use pointers? What is an application of pointers? And I think most of you use Spotify, and Spotify use pointers heavily. So Spotify has about 700 million users, 100 million different songs, and about 4 billion playlists. So in each playlist is, on average 100 songs. So let's say we have here our playlists, and in each of these playlists, so in each of these 4 billion playlists, there are 100 songs stored. That would be a lot of memory consumption. So, do Spotify really store these 400 billion songs? No, of course not. What they do is they have one database with every song once inside. And each playlist, so here are my playlists again, just have a pointer to the song. So the cool thing is now, so a playlist is just a collection of pointers with, let's say, 8 bytes. In contrast, if you would have a playlist with the actual songs stored inside, every song is about 10 megabyte, so it will be huge again. But if you use pointers, as Spotify does, it's way more effective and use way less memory. So this is just one example where pointers are very, very useful if you use them once at different locations, but always access the same element, in this case, one song. And the cool thing is, obviously, a song cannot be modified for a user, so every user should access the same song, of course. Okay, let's continue with the recap. And we have 2 questions prepared again. This one is about strings.
And it's, I would say a bit tricky. So I took a look at it. So you created the quiz, and I didn't choose the right answer.
You made it wrong? Okay.
Yeah, I did it wrong. So take your time, take a close look.
So we have 2 names here, 2 character arrays, David and Daniel. In the first printf, we compare the element on index 1. The second printf, we use str compare, and then we compare name 1 is equal to name 2. Question is, what is the output here? This might now also create a second question. What is the output of a comparison if you do it like this or like this?
So we've briefly talked about that already, but just to recap again, if we have a comparison, let's say, for example, name 1 at the position 1 is equal to name 2 at position 1, this is an expression that can either evaluate to 1 if it is the same character in this case, or it can evaluate to 0 if the characters are not the same. So each expression can, if it's in comparison, for example, evaluate to 0 if it's false, or 1 if it is true.
Yeah.
So that's why we also print the integer value here.
Okay, let's wait for another few seconds. Yep. All right. Yeah. Wow, great. So you made it wrong.
Yeah, I made it wrong.
So what did you make wrong here?
Yeah, I didn't look through the code carefully enough, so I made a mistake in the line of string compare. I read string compare name 1 and name 2.
Yeah.
And yeah, that's why I couldn't get the second integer value.
So the first printf here, name 1 on index 1 is equal to name 2 index 1. So we are basically comparing this A here with this A here. That's true. A is equal to A. That's why the first printed number is 1. The second one is str compare, which compares name 1 with name 1. So it actually compares itself with itself. It compares David with David. And str compare does really compare all of the characters inside of a string, but str compare returns 0 if they are equal. Yeah. I don't know why.
It is like that.
It is like that. So that's why the second number which is printed is 0, and the third one is also 0 because we are comparing here name 1 is equal to name 2, and we have seen last time and also in the practicals, when we write it like that, we are comparing not the strings but the pointers, and these are two variables on different memory locations. So they have two different addresses. So we are comparing the addresses here, and the addresses are not equal. That's why 100 is the correct output here. Okay, second question. We are missing one line here, and we want to print 21. What is the missing line? So if you listen to the practicals for today, this should be manageable to solve because they actually had this example or the swap example, but it's very similar today's in the practicals. So let's see what you said. Yeah, great. So increment and the ampersand age. So we need the address of age to hand over to the increment function. There it get dereferenced, so that we get the value of it, of this age. We increase the age by 1, So we actually modify this H here, and that's why this is the correct line. Okay.
Very good results. So
yeah, I'm impressed. Maybe it's too easy.
Maybe.
But we will continue today also with a few further and harder topics. But first, we have something missing from strings from last time, which was already discussed in the practicals. But I think just for completeness, we have to discuss it also here.
So yeah, since we didn't manage to talk about all the functions that we can use when we use strings, we just have a few slides for that. First of all, we've already heard it today, but so far we have used scanf. It's good. We could use it. It worked as we expected and wanted it to work. But of course, there are some limitations when using scanf. We've heard it in the practicals. For example, you're required to have some formatted text as an input so that it can be read by scanf properly. And that's why we also suggest to now use getchar or even fgetS. We'll come to that in a second. And with that, you can, for example, getchar, you can read one character and another character if you use getchar again, and so on and so forth. So this is definitely very beneficial if you, for example, have an input of an arbitrary length. But not only getchar can be used, we can also use multiple characters using fgetS. So again, we have the function definition here and the declaration. So the first parameter that is expected is the character pointer, which is the string you want to store the input in. And the second parameter is the number of characters that should be stored in this character pointer, so in this string. And what we have to take care when we use fgetS is that this already includes the null byte. So we can only read actually n-1 characters, and the very last character is the terminating null byte. And yeah, we just have a standard in here. We can just use it. We will talk about it in
a few weeks.
Yeah. So it's totally fine to just use standard in. For the moment, there can be also something else than standard in. But yeah, getchar or fgetS are definitely way better options than scanf if you have an input of arbitrary length. All right, and I think that's already that we have all that we have for strings. And now we come to one very important topic, which are, if you're doing your practicals, also relevant for assignment 2 already, which are command line arguments. And most of you have used command line arguments already, so I assume most of you have already used them. If you, for example, compile your code and create an executable program out of that. For example, if you use Clang, you use this command Clang, and after that, you just add another, let's say, words in this case, -w_all, -o, my program, and then the name of the file which contains your source code. So we have one command at the very beginning, and after that we have some arguments. So that's why it's called command line arguments, because you add arguments in your operating system's command line after the command, so after the program that you want to execute. And we can also do that with programs that we program ourselves. So when you execute your program, you first write the name of your program that you have compiled already, and after that you can just add as many arguments as you want. So we can see here that we have 5 arguments, which are just numbers from 4 to 9.
6.
I'm sorry, thank you. 6 numbers. We could have 60 numbers, so it doesn't matter. We can add as many arguments as we want.
And also text. So it should, not only numbers, also text.
Of course, yeah. It can be numbers, can be strings. So you can add just as many arguments of any data type as you want. And why can we just use command line arguments? Why do we need them? We can provide additional information when we execute the program already at the start of the program. So we will see on the next slide the main function, which is a very interesting, very important function that can receive all the command line arguments that we pass to the program via the command line interface here. So let's take a closer look at the declaration of the main function. I think we haven't used this one here in the lecture so far.
Not in the lecture. Yeah.
So we are familiar with this declaration here. So we use int main, and we just add void as parameters because we do not expect any arguments. We don't want to work with the arguments that may be passed to the program. But from now on, we can use them and we can work with arguments that are passed as soon as we use this function declaration of the main function here. So we can use these two parameters that are shown here, the argument counter and then the arguments, so the argument vector, but yeah, it's just the arguments which are character pointers to, so actually strings stored in an array. So we just have an array of strings as our arguments, together with the first parameter, which is the argument counter, which just tells us how many arguments were passed when we executed the program. So it's really cool that we can now use all the command line arguments that were passed when executing the program. Now let's take a look at one example. For example, we want to have 3 command line arguments here. Let's say you want to add 2 numbers, 4 and 6, and we want to add another argument, which is just a string, hello in this case. So how can we access these arguments, and how can we, for example, even print them? It's actually the same as for any other array that you use. If you pass an array to a function, you should also pass the length of this array so that you know how many elements are in this array. And this is actually what the argument counter is for. So you have here the number of arguments, the number of elements in this array here. And if you want, for example, to iterate through the arguments, the array of arguments, you can just use this argument counter and then access all the arguments by the index of operator. And yeah, this works like any other array that we have already discussed. So if we, for example, execute this program with the 3 parameters, we will get the following outputs. But why do we have now 4 arguments? Because we've only passed 3.
Yeah, so the first argument is always the program itself. So we call it like this here. And my program, as you can see also in the output, is the first argument passed to the program. Not very intuitive, and I haven't had any use case where I really used it, but maybe there are some use cases.
Yeah, but it's true in every case. So whenever you use this argument vector, so the argument values, the very first argument, so the first element in this array, is always the name of your program as you have executed it in the command line. And after that, all the actual arguments that you have passed to the program are then stored. And yeah, we can simply access them, we can print them. And what's important here is, we can also see it in the output, that all of our arguments are stored as strings, even if we pass, for example, a number which is 4 or 6 in this case. The main function always receives an array of characters. So even the number 4 is just an array of characters which contains 4. So it is a string, and we don't really can work with the string if we want, for example, calculate the sum of the first and the second argument. So we have to do something here. We'll come to that in a second.
There's one question.
There is one question, yes. That's a very good question. That's one thing that we will discuss today. So the question was, why is the argument vector a character pointer array and not only a character array, as I understood it? Yeah. We'll come to that today, but essentially, you do not have a character array, but you do have a character pointer array. So you store an array of character pointers, you store an array of strings.
So a string is always a character pointer.
Yeah.
And if you have multiple strings, you need an array for multiple strings. So you have an array of character pointers. So an array of strings. Separated by, in this case, here a space. So this one is the first string, or this one is the first string, second string, third string, fourth string, and so on. And to store multiple strings, you need an array again.
Because if you would only have a character array, you would only have a sequence of characters, but you wouldn't know what's now the first argument, what's the second, and so on. So
you probably have to split it by hand, by spaces, but the program does it for you.
Exactly, yeah. Okay, then also one very important point here when you're using arguments, command line arguments, is that most of the time you want to check if there are enough arguments that you would expect in your program, or if there are, for example, too less. We have the case here that we want to check, okay, if there are less than 2 command line arguments, we just return some value and do not execute any more code anymore. So you want to check before the actual logic of your program starts if there are enough arguments that you might use or want to use in your further code. So that's why we want to check first in the main function when you receive the command line arguments, is the number of arguments what we expect, or is it too less? And we can, for example, just return some code in this case.
Yeah, and the cool thing with that is we can now call our function with different configurations. So especially when we create our test cases, we can say we want to have your program in a specific state given by a parameter we hand over when we call your program, and you have to then deal with that specific state. So for example, we will come to that later in a few weeks, but we will maybe hand over configuration files, so really a config file, as a parameter, and you then have to read from this file. So it adds a lot of possibilities also for us to test something. So yeah, that's a cool thing.
Yep.
And one more hint, always, as I said, always check for the number of arguments. I think that's always one test case.
So yeah, as you already said, you can have different behaviors depending of your program, depending on the argument. For example, if there are, let's say, 10 different configuration files, and your program should behave differently for each configuration file, this is a perfect use case for command line arguments. Okay, so we can work with...
That's basically also, sorry for interrupting, but that's basically also what Clang here does. So Clang is just a program, but based on the arguments we hand over to the program, it behaves differently. So it reads our program, creates an object file or whatever. It enables all the warnings. So based on what we add as arguments, it does different things. That's a cool feature.
Yeah, and it's essentially just a variable. just a variable that is a character pointer array, so a string array that you can use in your program. So just a normal variable as any other variable in your code.
But we have one problem here. So as you said before, everything here is stored as a string. Can we convert it to integers if we have 4 and 6 here?
It would be great if we could do this, and yes, we can do this. So there are some functions already provided in the C standard library. You just have to include the stdlib header, which we'll use from now on, I think, every time, or most of the time. And in this header, there are already functions, for example, a to I, which means ASCII to integer, which converts a string to an integer. So you pass a string to the function to a to I, and you will return the integer value. So if you, for example, pass 1 as a string, you will get 1 as integer value returned by this function. You can do the same also for float values. It's just another function. It's a to f in this case. Again, you pass the string of the float value to the function, and then you will get the float value with the data type float back from this function. But yeah, okay, we can use this function, but they're not very, I would say, intuitive, because they return 0 if there is an error. So for example, if you pass the string hello or any other word to a to I, you will get 0 as a return value from this function. And how can we distinguish if it's just an error or if we want to pass the string 0 and we want to convert this string 0 into the integer value 0. For that, we could use, for example, str2l, which is the conversion from strings to longs. And a great benefit of this function is that it has, I would say, a bit more advanced error handling, because you won't get 0 as the return value if there are any problems when trying to converting a string to a long value, but you will get some very high, for example, number that you will most likely not reach or you don't want to use in your program. And there's also a bit of a difference in the function declaration here. So you don't only pass the value, so the string that you want to convert, but you pass the pointer to the next character after the number. And this is just null if there's nothing behind, and else you just set the next character, the pointer to the character. And also, that's a good question. I just noticed.
I just saw it, that here should be, of course, a float.
Thank you for bringing this up. Of course, if you use a to f, it should be data type float for the variable where the value is stored in. Thank you again. And one more additional cool thing about the str2l function is that you can also pass the base that you want to have it converted to a long value. So in most cases, we will just use base 10, so we just pass 10. But of course, you could also use hexadecimal values, so you can pass 16 as the base and also other bases. So that's a very cool function, actually.
Yeah. Okay.
All right.
That's. Let's finish with command line arguments, and let's go back to pointers and strings. And already at Tanya and Michi did a lot about the similarities and differences of strings and pointers. But we want to have now a few slides again. What are exactly the differences between strings and pointers? So when we look at the data type and all the sizes, we already found out that strings, the size of a string is always n plus 1 byte, and n means the number of characters inside, plus 1 for the null byte. If we have a pointer is always 8 byte long, no matter what it is pointing to, if it's an integer, a string, or whatever, it's always 8 byte long. So that's one difference. Let's assume one more time this is our memory here. It starts with 0 and then goes, it goes further, of course. But here is our string hello, starting with 0x9 until 0xe. Let me just rewrite it to this formulation. It's a bit easier for us because we also have the decimal formulation here and we also have the index here. When we execute it like this, so I have my string as an array, write hello inside, and then I write size of my string. What's the output of this first one here? Any ideas? Just say it if you have an idea. Sorry? It's 6. 6 because it's an array and it just counts how many elements are inside 1, 2, 3, 4, 5 and the null byte. That's why it's 6. So the size of this character array here is 6. But there's a difference if I write it like this. So I have again my hello string here, but now as a char pointer, and I call again size of my hello. What's the output here? Yeah, 8. Yeah, because a pointer is always 8 byte. And one more thing, if I have my string hero again as an array, as we have seen here, what I call strlen. What's the output here? 5, yeah, because hello is just 5 characters, so strlen does not include the null byte. So you can see the same string, 3 different sizes, so you have to be careful what you are using. And this is also one of the most important differences between arrays and strings. So the size of it depends on what you have, how you defined it. If you define it as an array, it is most likely what you want to have. It is the number of characters inside the string plus the null byte. If you have a pointer and you use size of, it's most likely what you don't want to have because this is always 8. And the strlen is pretty similar to the array, but it's always 1 less because it does not include the null byte. So the differences between strings and pointers are, okay, of course, how I write it, yeah? I use this notation here to create an array. I use this notation here to create a pointer or a character array, a character pointer. One is an array, one is a pointer to the first character, but the most important one, the left one can be modified. The right one cannot be modified. We will come to that in the next slide, why, and I think next week we will discuss it even further, why it cannot be modified. And as we have seen before, the size is defined by the base of by the length when we have an array, and the size is always 8 when we have a pointer. These are the main differences, and you have to consider that if you're working with pointers and arrays. Okay, so what happens if we want to modify a character pointer? So the first version works. Yeah, this is a character array, and I can modify the first element here. This works. The second one, if I do this, I get a segmentation fault. And as I said before, this character array is not stored on the stack where so this character pointer, is the second version here, is not stored on the stack as this one is. It's stored on the so-called data segment. It's a different segment in the memory where we cannot modify the value. We can place it there once, we cannot modify it then. That's why the second version cannot be modified. And that's also a huge difference when we create such a pointer or a character pointer. We always have to consider, do we want to modify that? Because then we need a character array.
And I would say that's a common pitfall or trying to modify a character pointer.
Yeah.
I think we have faced this issue, all of us, I assume, at least once. So if you want to modify a string, you should or you have to use a character array instead of a character pointer.
Yeah. Okay, we have a quiz for you now. Few lines of code. We want to copy the name of my variable name into a new string called new name. The question now is which line or which lines contain errors?
Yeah, and maybe as a recap, last week we talked about str copy. I think we also mentioned str ncopy.
Yeah, so str ncopy is just like a bit of an improvement of str copy. We can additionally, as a third parameter, hand over the number of elements we want to copy. So here the last parameter here is the number of elements we want to copy from this parameter here, so from name to new name.
Again, I think it was not that easy in my opinion, but
it's not that easy, yeah. And
let's see.
I already see the tutors scratching their head. That's not the best way to write code, I know. Okay, let's see what you said. Line 8 has a problem, yeah. Line 7 too. Let's go back. It's this one here has a problem and line 8 has also a problem. Let's switch to VS Code for a second. I think that is it. Yeah. So if I execute it, okay, I get some warnings, but that's fine. I get a segmentation fault. Why do I get a segmentation fault here? So, okay, the first thing we should talk about is this one. We have here a character pointer and do not write something inside. So this is basically a pointer we create, so a string with no content.
But it's a string.
So. It's a string, but it's nothing inside. So how large is this? Yeah, we have a pointer to nothing. That's not good because we want to copy this string inside. That does not work. So we have to at least say, for example, create an array, write nothing inside, but now we have space for 20 characters, for example. Let's try it once again. Okay, so it works now, but it's not fully copied. it stops after the du here. And that's the problem of this line of code here, because size of name is, as we say it so often, it's just 8 because the size of a pointer is always 8. Name is a pointer. So what we need to do here is, or in this case, only the first 8 characters are copied. So what we need to do here is, for example, use strlen of name. We need to add +1 for the null byte, because strlen does not account the null byte. Let's do it once again. And now it is copied and it works.
Perfect.
So this is just one short example why you should be very careful when creating the pointers instead of arrays, especially when you copy something inside. So you're actually modifying it. You should create an array instead of a character pointer here. Okay, any questions to this? If not, then one more thing. Let's go back to our memory here, where we have our hello string inside, and we also see here in the end our terminating null byte. This now works also for character pointers, but let's say we create again our string here as an array. And this is what Michi told you today in the practicals, and it's very, very important. I now access the 0 element, first element, second element, and I also access the address of the 0th element, first element, second element, printed as a character and as an address. So the first thing here is my string index 0, which is an H, and this one here is the address of the 0th element, which is the address of H, which should be OX9. But one more thing to mention, when I use just the string here, so just the variable name and dereference it, so this is the output, it's the same as the second line here. So dereferencing my string means we are dereferencing the string, so the variable here which points to the first element, and my string is a pointer here to OX9, or to the, it contains OX9, which means it points to the variable H, or to the value H. And this is exactly the same as the second line here. It is my string at index 0, which contains H, and the address of my string at index 0 is also OX9. So there is no difference between the 0th element and the string or the variable name itself. The first two are equal. When we go all over the other ones, we can see, for example, my string at index 2 and the address of my string index 2, they are pointing here to the L and to the address of L. That's why we see here the output like this. We will come to that also a bit later once again. But the important thing is here, the variable itself always points to the first element. And then it goes until it finds a null byte. What if we cannot find a null byte? So what happens if there is no null byte at the end of our string? Let's try it out. We have again our hello string here. We have here our null byte. That's our code. Yep, that works. We have here hello with the size 5, so I have here my string. So the string is printed, and with the second parameter here, it's a long digit, but its string length gives us a long, but that makes it's useless here in this case. Strlen of my string is 5. Strlen, when we remember, just counts the characters until it finds a null byte, works. But now let's override here the null byte with an H, for example. So we override the null byte here, and then we print out the string once again. And what the program does now is it goes until it finds the next null byte. So it prints this H, E, L, L, O, H, F, E, $, null byte. Oh, okay. So it terminates here. So the size now is also 9. You can see here it's hello H, F, E, $. And just because we were overwriting the null byte, I don't want to say that you should do this, but we can practice a bit with that. So especially in later courses, you will somehow exploit the programs and try different things to maybe manipulate programs, user input and whatever. And this is just one very, very easy way to see what's in the memory, because just print it out and overwrite the null byte and you see what's in the memory after your string.
So we can access memory locations that we shouldn't be allowed, or at least we shouldn't do it.
In a certain border, yes, we can do.
That's interesting.
But I think there will be something in the practicals in the next few weeks where we'll exploit a bit more about the stack. Do you still have included some exploits of the stack in the practicals? Not? Then in other lectures. Okay.
For the moment, enough pointers, enough strings.
Pointers. I want to now have like a short break in our minds and talk about algorithms in general and thinking like a computer, because that's something you are currently in a process. Yeah. So you learn now like conditions, loops, whatever. And I want to give you an idea what an algorithm is, because you will from now, or you maybe also already have applied some algorithms, but you will apply algorithms in future, of course, and also in the next assignment. And one algorithm I want to visually show you now is, let me call Sebastian. Okay, I can do it with my phone. Yeah, obviously, everybody can do it with the phone. We have a contact list in the phone, and in the phone there is most likely a search bar of your contacts. You can type the name, and magic happens. His name occurs, and I can click on his name. But how does this searching work under the hood? This is an algorithm, and I don't know who remembers this one. This is like a hard copy phone book. But it's very, very good to show you how algorithms work in general. Yeah. So let's say I don't have a phone, and let's say you are in this phone book here. I don't know if you are inside, but
I haven't found myself, so you could try it.
One very, very easy way to look for him is, no, please just stay here because I need the alphabet.
Ah, of course.
One very, very easy way to look for Sebastian is look at the first page, look at the second page, look at the third page, look at the fourth page, and so on. Will I find Sebastian? Yeah, sure.
At some point.
It's at some point, yeah. If I pay attention to the names. So it's a correct algorithm, but it's not very, very efficient, because when when you have a name with, I don't know, X, Y, Z, it's a lot to do. Even this is a very small phone book, it's a lot to do here. Okay, let me improve that. Let's say I have a look at every second page. So I always skip one. So this one, 2, 4, 6, 8, 10, and so on. Is this algorithm correct? So will I find him? Yeah, maybe. When not? Yeah, if his name is on a page where I skipped him, then not. But I can easily fix it. So as soon as I'm too far, I can just go one page back, and then I've found it. So it's an easy fix for a wrong algorithm, and then it's correct again. This now is correct, and it's 2 times faster than my first algorithm. But it's still, of course, not very, very efficient. Yeah, it's half of the time, but it's not very efficient. This is called a linear search. What usually is implemented when you search something is a so-called binary search. And it works like this. So your last name is with G. No matter where your last name is, I open the book in the middle. Okay? Let's say we are at O. Yeah, O is somewhere in the middle. Let's say we are O. Is G on the left side or on the right side? Left side, yeah. So what we can do now is remove the right side, and I have halved my problem. Let's do it once again.
Mm-hmm.
Okay. It's already breaking, yeah, but open it once again. I am at H.
Probably, yeah.
H. Is H on the left or on the right side? Where is G from H? Left side once again. So again, half my problem and open it once again. And you can see a pattern here. Let's say I'm at D now. Where is it? Right side. So remove the left side. And I can do this as long as I am then on the page where I can find him. This now took me 3 steps to come very, very close to his last name compared to, I don't know, thousands of steps maybe it would took me if I go page by page. So this is a correct algorithm and very, very efficient. And this should show you now that we do not demand you to implement the best and the most efficient one. But there are efficient algorithms and not so efficient algorithms. And in your studies, you will come to a certain point where you need to implement efficient ones because it's about runtime. You have to have your program very, very efficient and fast because then your program is better than other programs. And I think that's what a good computer scientist separates from an average one. So let's go through that in pseudocode once again. We have our name. What we have done is we looked at the middle page of our current phone book. If we found the name on that page, we are already finished. If the name was not found, we choose our new search space. So if the name was earlier, then we use the left side. If the name is later in the alphabet, we use the right side. And then we go back to step 1 and again look at the middle page of the current phone book and see if the name is here and so on. We can also visualize that as a flow chart. It's the same as we have seen before. Look at the middle page of your current phone book. Is the name on the page? Yes, then we are finished. If no, decide if it's on the left or on the right side, and then start again, look at the middle of your current phone book. That's an algorithm, and that's the flow chart of the binary search algorithm. There are many, many famous algorithms, and that's just a few which you will now see maybe for assignment 3. You have to find an algorithm for searching, and you have to find an algorithm for sorting. it's not that easy to implement. Not that easy, but always, yeah, let's say not that hard. It's okay for first semester, I think. Yeah, because I implemented bubble sort in the first semester, and linear search is also not, it's basically just a follow.
Yeah, it's doable.
It's doable. So you need to implement some of these algorithms in assignment 3. Of course, there are many, many more algorithms, but that's just a short excerpt.
And I think you will even need them in homework, the homework of coding session 2.
Yeah.
So we'll also get in contact with search algorithms there if you're doing the practicals and you're planning to do coding session 2.
Yeah. And you also might have seen algorithms also in series. So I love Big Bang Theory because they teach you science in a very, very interesting and funny way. And Sheldon had this friendship algorithm where he created an algorithm to be friend with somebody, and he created a flowchart on it. So that's basically the perfect way to start an algorithm, and then we can implement that.
I don't know if it's the most efficient one, but
but I think it worked in the series. Yeah, so why not? Okay, let's be a bit more serious now after this algorithmic thinking journey. Let's go back to arrays and pointers and how we can access them. So let's say we have again our array here, and we are now talking just about different representations, how we can access arrays and pointers. So what we know is we can access an array like this, so data on index 0, data at index 1, index 2, and so on. All of them has a value, and all of it has an address. So it's stored somewhere in the memory here. Note that each of them, because they are integer, use 4 bytes. So the first address is 000, the second one is 0004, next is 8, Z, 10, and so on. So it's always 4 bytes. So we know this, but what we have seen a bit, but we want to discuss it explicitly, is we could also calculate with these pointers. So what we can say is data, as we know, now this is basically a pointer to the first element. So it points to, in this case, OX0000. But we can calculate with this value, with this address, and say data plus 1. And what the program does now is it increments by 5, so by the size of the integer, because it knows it's an integer array. So when I write data plus 1, I end up with the address OX0004. Data plus 2 is OX0008, because it's an integer array, and when I increment it, it's always adds 4 bytes. And we can make use of that. So there are 2 ways to basically interact and write or access pointers and arrays. We have seen the second one, but this is just an alternative one. So we can write data plus 1 and then dereference it, and we come to the same element here. So data at index 1 is 5, and data plus 1, so data is a pointer to 90, data plus 1 is a pointer to 5, dereference it, and I come to 5 to the actual value, and I can output that. So I can also write this like dereference data. I could maybe write the data plus 0, but it makes no sense. Data plus 1 and dereferenced, data plus 2 and dereference data plus 4 and so on. And I can access again the same values. Why should I use it? It looks a bit more to write compared to the index. Sometimes it's easier when you iterate over arrays to just increment a pointer pointing to the first element, second element, third element, and so on. And then you can write it also like this. Yes? Very good question. Does it make a difference if we leave here this parenthesis out? Yeah. So dereference data plus 1 would make a difference. Yeah. So in this case, data is incremented by 1 and then dereferenced. Yeah.
I think that's even part of the next quiz that we have. So
yeah.
We can explain it even more here then.
Let's talk about it after you solved it.
But yeah, maybe to mention it again, as you already said, David, it depends on the data type you have in this array, how many bytes are added for adding value 3 or any value. So all the time, n times the bytes of the data type are added when you're using pointer arithmetic. So if you would have a character array, only 1 byte would be added if you have, for example, +1, because a character has the size of 1 byte.
Okay, last few seconds. Let's see what's your solution. Yeah.
Well,
I shouldn't have give a spoiler. Credit to the guy here who made me say the solution already beforehand. So, but let's just go through once again because it's very, very important to understand. So the left one here means we have our pointer to the first element data. We add 3 times 4, so 3 times the size of the integer to the data, which means we go from 90 to 5 to 7 to 10. So we increment the address and then we use the asterisk to get the value 10. On the right-hand side, we dereference data because this operation is done before we add 3. So we dereference data, so we get the value 90, and then we add 3, so we end up with 93 as output. Very important. So again, if you're unsure which operator is executed first, just use this parenthesis because you're in the safe way and it's easier for you to understand. Use them one more time than one time too less. Any questions to this? Okay, we are very good in time. I think we have 2 more topics. One is there are some very, very special pointers. Mainly we will use them, or one of them next week.
So usual pointers are not enough. We want to have some special pointers. For example, a null pointer. We have already heard it today. In the practicals, we have seen that we can just write null in our code here, for example. It's a valid pointer. You can do this. You can compile your code. This will work. However, there are some special use cases when you want to have a null pointer. So basically the value null that is assigned to a specific pointer. For example, you want to store null if you just want to initialize your pointer variable, but you don't have an address already that you want to store in the pointer. So you just initialize it with null, and you can then change it later in your code. But I think even more important is that you can and you will use null pointers for error handling. So we will, have you already learned functions that will return null? I don't think so.
I don't know if we had function that return fgets.
Thank you.
Ah, yeah.
We have, of
Thank
course.
you.
Yeah.
Yeah.
So we talked about fgets, and fgets will return null if there is an error, if there occurred an error when trying to read the input from, let's say, standard in.
What's the difference between null and 0?
It's a very good question. Actually, there's not really a difference. There is, but it's just a convention, or it's say so. You should always use null if you're using a pointer and compare a pointer with the value 0, but just write null because that's a convention, or just I would say every C programmer will do this.
Yeah.
So if you have a pointer you want to assign the value null, so 0 actually, but null, you just use the keyword null. Also, when you compare a pointer with the value null, for example, again, you do not use 0, but null as a keyword. And so fgets, for example, returns null on an error, but we will talk about many other functions that will return null. And this indicates that, okay, something didn't go right. We have to handle this specific case that the function call didn't do something as we expected it to do it. So that's one, or I would say the most important use case of null pointers. But we already talked about it last week. We can also have a pointer. So last week we talked about just creating a pointer variable here. So just storing the address of a value of a variable as the value of the, in this case, integer pointer. That's totally fine. We can just, for example, dereference it and get the value of the original variable. But we can also now store the address of the pointer, and this is, again, valid C code, compiles, it runs. It's even required at some point. And we can now just write 2 asterisks here, and we store the address of the integer pointer, which stores the address of the integer variable, which again stores the value, in this case, 42. And if we now want to dereference the pointer to actually get the value of my variable, so to get the value 42, we have to dereference it twice, so we have to use 2 asterisks. Also, if we want to modify the value of my variable, we have to use the dereference operator 2 times, and after that we can actually modify the value of my variable. So we go away from pointer 2, which stores the address of pointer 1. We dereference it. Okay, we can now go from pointer 1, or the first pointer, to my variable. And if we dereference it again, we can now retrieve the value 42 of the original variable that I have initialized here.
If you now think, why should I ever use this? It's very, very common, to be honest, to use it, because think of arrays of pointers. So think of, you have a string is a pointer, and then you have multiple strings, and that's already an array of strings, and an array is also a pointer. So you already are here at a pointer. So an array of pointers is a pointer. So that's very, very common. Let's say we have here an array. So we have here a struct. I think we had struct in the beginning, and leave them out for now for some time, but we will need it in the next few weeks. So if we have a struct here again with a name and an integer grade, so this is a character array and an integer grade, and here we already have some kind of a pointer, because this one here is just an array with 10 students inside, but not with students inside, but with pointers to students inside. The second class here is a student array. So in this case, we actually have 10 students inside. Not the pointers, but the students. This is kind of just a teaser for the next lesson, where we will use this more and more. But there is one difference. So the size of a student is always the sum of all of the individual elements in the struct. In this case, we have 28 and 4, which is 42 then. And if I calculate, let's move on to this one for a second. If I calculate now the size of an array with 10 students, and each student is 32 bytes long, so 28 for the name, 4 for the grade is 42, times 10 elements I have inside in my array, it's 320 bytes. That's why the output here, the size of this array of students is 320. But if I have an array like here of student pointers, pointers are 8 bytes. I think you have it now. Pointers are 8 bytes, so I have 8 bytes times 10 elements, because the array is 10 elements. So this one is 80 bytes long. And this one, so this class 1, can already be seen as a pointer, because it is an array of pointers, and arrays are like pointers. So basically class 1 is a pointer here. I think we should leave you now with the confusion, because it's a good cliffhanger for next week, where we talk more about these arrays of pointers, memory, and also dynamic memory. Yeah.
But so far we're done with pointers. We will now really apply them. So if there are any questions, let us know, ask on Discord, because we really need to understand pointers, because we will apply them from now on in the following lectures.
Okay. Thanks for being here, and see you next week.
See you. Bye.